Non, c'est juste que... En général, c'est juste que... Non,
maintenant vous avez deux accès.
oui.
Mais en fait, c'est juste que c'est meilleur en termes de taille, en général, c'est la plateforme.
I'm gonna go, but if you need anything, let me know.
Thank you very much.
Thank you.
Bon number, vous êtes relié pour ma quelque chose.
Oui, oui, d'accord, on va faire. Ok, oui, parfait.
Dirigez vers l'avant, comme c'est les embauches aussi. Quelque chose d'un peu haut là qui signale l'arrivée de... Ouais. Genre Bob. Ça enregistre ça? Oui, ça enregistre. Vous avez trouvé quelqu'un qui veut si je peux revenir par là, si vous pouvez voir quelqu'un qui est fou.
How you expect me to talk about the work itself, or what else you want me to talk?
Yeah, just to talk
Briefing the work itself, right?
I will just put this.
Sure.
No, let me, because it's a little
Okay.
fragile. But there.
I can put my phone here. Okay.
Thank you.
It's okay. Okay, so am I supposed to talk now? Yeah, sure. Okay. So this work is about the big allocation for visual facial quantization. And the visual facial quantization is for the transmission between data transmission between edge and cloud side to enhance the collaboration between the smart devices in the edge and the cloud side servers. So for the feature compression, the quantization method is quite important. And this method is to develop a big allocation method for such visual feature compression purpose. So in this method, we use some statistics of the data to help to decide which channel of the feature should be put more bits and which channel should give less bits. So it can overall give an optimal performance for the compression and the fidelity of the data. So you can more efficiently to transmit the data for the edge cloud collaboration tasks. For example, like auto-driving cars and also image classification, detection, and segmentation, and etc. So that's about the work and the background, how you may apply the method for the real-world tasks. So anything else I need to say?
Perfect.
Thank you.
Thank you for your help.
Thank you.
Thank you very much. What?
Demander à quelqu'un, mais quand tu lui avais demandé
En fait,
comment dire, c'était quoi?
Attends.
Non, si moi en fait je lui ai déjà demandé, t'as pas besoin de lui redemander du coup.
Demandez quoi?
Tu as mis en mute?
Là, je l'ai démonté. son est on.
Yep.
C'est possible même de le mettre.
Okay. Hi. Can you hear me? Can I go? All right, should I start? Yeah. Okay, so hi everybody, this is Davide, and today I'm presenting our work. The context is face anti-spoofing, so if you're not familiar with it, when you have a mobile phone and you want to unlock your phone, it will look at your face and it will try to detect if you are the right person, but also if you're a real person. That's the anti-spoofing part. And what we're looking at today is a way to improve existing solutions where we make sense or make use of temporal data. And that's basically simulating the real scenario where a user will interact with their phone for the whole lifetime or for years. And in that case, you would like your phone to learn what you look like. Namely, if you have a certain facial characteristics, the model should learn to distinguish if you are the real person by interacting with this phone, not just any other person. And the way we do this is by having a model defined by two components. The first one is a feature extractor, like a CNN, where the heavy computations are done. And then a small classifier in the end, 1-2 layers of linear layers, so MLP, which is the classifier. And we want to adapt the classifier using past online data from this user. So this is basically the online inference. When a new sample is seen by the model, prediction is done, but also this sample is used to fine-tune this small classifier. And the way it's done is through this online adaptive personalization component, which is the main contribution of our method. And basically it's as simple as storing some experience replay for the specific user and use it to fine-tune the model to improve the performance for the specific person. Imagine that the person over time shaves their beard or changes a bit in appearance. The model will learn to adapt to it because it sees and fine-tunes on this kind of data. And overall, when we evaluate, for example, on different videos from the same person, we start with live videos and then spoof and then live and then spoof. We say that the model can quickly learn about this person, improve the prediction scores, and then also adapt to a change in the context when the spoofs are seen, and then again live and spoof. And yeah, that's pretty much the idea of the work. We show that it works better on 3 different protocols on the spoofing in the wild data sets. And we also have some techniques which really help making the solution work better in the real scenarios, and yeah, improve over this standard approach where you plug and play a continual learning method. We basically have some techniques to improve the robustness over time, and also to prevent the catastrophic forgetting by using some pre-training data during the online fine-tuning. Thank you very much. Is it good? Can you hear?
recording.
Or you put it on.
If you just can go like it's from there.
Okay.
You can start it.
Yeah. Okay. So.
Yeah, I'll just repeat my question.
Yeah.
So we have this like point cloud, right?
Yeah.
And here you say that this cloud of points can be represented by a cosine, like sum of cosines, right?
Yeah. Yeah.
And I mean, why? What is like?
Not.
Okay, so for example, if you think about a function, so not every function can be represented by a sum of frequencies, right? So the function has to be periodic, for example, so it has Fourier series.
Yeah.
So the reason, because the function is periodic, represented as a sum of complex exponents. What is
Yeah, so our assumption is that you can also, you can do transform this signal into a spectral domain.
yes, and then what you will see.
Of course, the problem here is that we're not discrete, so we cannot directly apply DCT. So we try to estimate how the spectral version of the signal would look like. And we make this by an iterative model estimation in the spatial domain. So
you don't
we do not
know the model. You
No,
iteratively
yeah,
the model.
yeah, right.
And this iteration has nothing to do with this upsample.
No.
So after you can upsample.
Yeah, right.
You can do
It's
a lot
just
of other stuff.
so here. Then I have a representation of the set
This is
coordinate.
just an interpolation.
Yeah, and this is just an interpolation to get the remaining two
And this is the
dimensions.
interesting part.
Yeah, this is the interesting part, and this has to be done.
Wow, this is very good.
Right.
Maybe I'll make it.
Yeah, of course. And you, I have my LinkedIn here, so you can also contact me, and you have my name.
Thank you very much.
You're welcome. So, any further questions? Can I explain something?
I usually follow the orientation.
Sorry to interrupt. Just
Okay. And this. Okay. Okay. I think I can start. Can you hear? Okay. So my work is about upsampling. Point cloud upsampling is very similar or is related to image super resolution, as most of the people know here. So the problem is how to insert additional points into a point cloud. And for that, we go for a local approach. So the first thing that we have to do is to partition our whole point cloud into smaller parts. And for these smaller parts, we chose blocks that are partitioning the whole range of the point cloud. And then for each block, we try to estimate a continuous the surface of the point cloud. If we found the continuous surface, to find the x and y coordinate of this continuous surface, as this continuous surface represents the z coordinate. This is done here on the right hand side. So we smash our block in 2D like a projection and insert the new points on the edges of the Delaunay triangulation. And we do this for all the single blocks here, put everything together in the and have an upsampled point cloud, which you can see here, for example. This is a scaling factor of 2. This was the original, and data or methods that use normal vectors like sampling perform worse than our FAQ that we put here at ICIP.
Thank you very much.
For what?
It was good.
For what purpose is this actually?
This is for the participants that are online for the ICIP
online.
Okay, so this is our paper, 3D self-permix, self-supervised learning for 3D point cloud analysis. Our main objective is to perform self-supervised learning to train a point cloud backbone to be useful for several downstream tasks such as classification and part segmentation. Our self-supervised learning does not require label supervision. Our main idea is that suppose that we have two point clouds, airplane and skateboard. We first use mixed sample data augmentation to mix these two point clouds to obtain the mixed point cloud. Next, we enforce the point cloud backbone to preserve semantic consistency between the partial airplane point cloud and the complete point cloud. From the network architecture right here, we can see that we have three aforementioned samples. We then follow by a shared encoder to encode point-wise features for each point cloud. We then perform mass pooling operation on the point cloud, so we could obtain the global feature of the complete point cloud and the global feature for the partial point cloud. Finally, we could use the self-supervised loss on these two vectors and enforce these two vectors to become similar. If the label supervision is available, we could use other two loss functions to improve the learning. The first one is the classification loss, which enables to predict soft label of the mixed point cloud. Another is point-wise classification loss, which distinguish the point. We conducted several experiments, including supervised learning, self-supervised learning, semi-supervised learning, and part segmentation. Our method is performed better than the baseline and state-of-the-art methods. In conclusion, the experiments show effectiveness and robustness of our method. Thank you. Thank you.
Thank you very much.
Thank you very much.
Just this. Okay. Thank you very much. The mic is on.
Hello, this paper is on face reconstruction from deep facial embeddings using convolutional neural network. In general, in face recognition systems, feature vectors are extracted from each face image and stored in a system's database. Then later, when a person comes for identification or verification, same features are extracted from the image and are compared to the ones stored in the system's database. So that being said, means that we have very important information stored in the system's database, and if an attacker could get these features, they can do some malicious attacks and get very important information from those features. What we show here is that the adversary can reconstruct face image from those features stored in the database of the system. So here you see our results. The first row shows the original images, and the second and third row show the reconstructed face images by our method or attack with features extracted with different models, arc face and elastic face. You see in this table the evaluation of our method. One thing I need to highlight is that our evaluation has been done on different databases. First, our feature extraction is trained on MSLab, which is one data set. We train our face reconstruction on another data set called FFHQ, but we evaluate everything on another data set. So we have a cross evaluation on Mobio and LFW. And you see here the results show that we achieve success attack rate of 100% and 96% for Mobio and LFW for arc face, for instance. In general, we propose a novel network structure and use multi-term loss function. And our ablation study also showed the effect of network structure compared to the ones proposed in the literature, which shows the improvement of our network structure. And also we use different loss terms, which each improve their reconstruction quality. And finally, the white box knowledge of the feature extraction model will improve quite a lot the success attack rate, which is something reasonable if attack knowledge about the feature extraction model. Thank you.
Merci beaucoup. Thank you.
De rien.
C'est bon? C'est bon? Yeah.
Merci.
Perfect.
How much time do I have? I got 3 minutes. Okay. Tic tac. Here. Okay. So my name is Carlos Cortés. I'm a PhD student from the Technical University of Madrid. This is my poster, Impact of Self-View Latency on Quality of Experience, Analysis of Natural Interaction in XR Environment. So the goal of this study is to determine the threshold in quality of experience of the self-view latency. This self-view latency is the motion to photo latency you have when you are trying to integrate your hands and some objects from your reality for interaction using image segmentation. So, a lot of people are using neural networks for this, but the neural networks nowadays have a problem. They add so much delay. So, what is so much delay for these kinds of environment? This study goes for it. Firstly, we create an environment where you can see your hands and the piece and some objects, and we use the minimum scenario, the minimum latency scenario for image segmentation, which is green chroma key. So once we have the minimum latency scenario, we measure the motion to photo latency that this scenario adds, which is the capturing plus the rendering delay. We use a system described in the paper to measure that minimum delay, and was measured in 190 milliseconds. Once we have that, let's go to the subjective study. We prepare by buffering delay a tunable latency adder for that experience. According to the literature, we selected 6 different delays, and we scanned 4 different figures for performing a block building task. During the experience, the user are seeing their hands, some blocks, Lego blocks, mega blocks, and scan 3D figures. So we take the 4 figures, the 8 delays, we mix them randomly, and we put the people to building the blocks, to reproducing the figures. After each reproduction with each delay, they had to vote a subjective questionnaire including 4 different factors: the adaptation, the haptic sensation, the global quality of experience, and the involvement. So, after the voting, we saw that the limit of acceptance, this is important, what people accept, not notice. They are going to notice even 250 milliseconds. But the people stands in terms of involvement and quality of experience, global quality of experience, around 450 milliseconds. However, if we go to the objective data, the time they spent for each delay, the average time they spent for accomplish the task, we can see that the people somehow adapted, because in these delays from 190 to 600 milliseconds of added delay, we can see no statistical significance between the average times. However, there is a clear trend that if I put you 2 seconds of delay, you are going to throw the head-mounted display to the floor. And also the subjective data says that for adaptation and haptic sensation, the people felt more or less acceptable for those delays. However, this was only tried for seated experiences not involving 6 degrees of freedom or social VR. That are the next experiment for the next ICIP. Thank you. Sorry if I... Well.
Sound is on.
Yeah. So our work is about brain aging, and so the way where explainable AI can help in understanding the results of our algorithms. So brain aging is about the estimation of the age of our brain with respect that is compared to the chronological age. When you face such a problem, you have to define your model, and your model depends on which features you use to estimate the age of your brain that we call endophenotypes. And in particular, we used MRI, magnetic resonance imaging, in different acquisitions. Then you have to choose the prediction model, so ranging from linear models, simple linear models, to deep learning, machine learning, and so on. And then you can apply some explainability or interpretability methods depending on the model that you choose, of course, to describe your data. Regarding explainability and interpretability, we have to refer to a taxonomy and to some definition. So interpretability is the property that allows you to understand actually what the algorithm does. So it's connected to the human intuition between the output of the models. While causability reflects our ability to understand what is going on inside the model. So these are two different aspects. Explainability is associated with the decoding of the internal logic, actually, of the model. So none of them are the same and are related to causability, but causability reflects the extent to which the explanation of a statement to a human achieves a specified level of causal understanding. Okay. I specify this because in the literature sometimes there is some confusion in the use of these terms, and so interpretability and explainability are used interchangeably while they are not actually the same. So we have here explained some possible models that can be used to derive the estimated age of our brain. Here is an example of what could be the complete pipeline. So the training of the model that can rely on different modalities. As I was saying, we were using MRI, but you can also use other kind of data. Then this model, of course, is tested on a different set of subjects with respect to those that were used in the training and validation. And then you can estimate a brain age delta. Brain age delta is the difference between the estimated age and the actual age. So the higher the delta, the older your brain looks with respect to your actual age. So what we could see here considering different approaches is that brain age prediction based on deep learning approaches have advantages because they allow to use big data to make these estimations. In particular, we are targeting the UK Biobank data that consists of 5,000 subjects. And then, in general, the more features you use, the better it is your result. So you reduce the gap between the estimated age and the actual age. And in particular, in our specific work, we could see that the features that were more important in this respect was the structural data, representing the deformation of some brain regions, and the diffusion MRI data, which provide information about the microstructure of certain regions of the brain. So this is more or less the content of our poster. Please refer to the paper that is published in the SPM magazine to have further details.
Thank you very much.
You're welcome. I'm not very good in this kind of
afternoon. I am Priti. I am from Indian Institute of Technology, Delhi, and also from All India Institute of Medical Sciences. I am here to represent our team, and our work is towards evaluating surgeons and giving them scores. So for different surgery, they need different skills, but in the current scenario, most of the skills training evaluation is based on subjective, that we don't have any automated skills evaluation system, especially for neurosurgery. Neurosurgery where the margin of error is very low, and if the surgeon makes an error, that means the patient may either die or get paralyzed. So in that case, the load for neurosurgeons being evaluated is very high. We want surgeons to be evaluated. We need an automated skills evaluation system. So we are working on two different data sets. One is a public data set, which is the Jigsaws. Another one we have developed in-house. It is a neurosurgery data set. And looking at the earlier work, we are looking at different surgical skill scenario or paths, we can say, different skill sets that we can look at is like tracking the surgeon, or like looking at the time taken to do the surgery, or the events in which like an adverse event can say having a low skill. But when we look at the SOTA, which is CVPI 21 paper, it could not generalize for our data set. And when we analyzed why it happened, we found that the evaluation metric is based on relationship between the score, which is the ground truth score, and the predicted score, which is the SROCC metric. And I'll explain with an example. We have a scenario where the predicted score is just a shifted version of the ground truth score, and the consistency is maintained for the rank. In that case, the mean square error will be less, but the SROCC will be good. But in a scenario where the rank has been reversed, but the score is very close, MSE will be good, but the SROCC will be bad. So we found that this is a scenario for most of the skills evaluation system, and we introduced a rank loss to penalize if there is an inconsistency in the rank. So this model works with a K rank loss. We take K videos and find out the ranks between them, and we added this rank loss along with the MSE, and we found that we are good with the Jigsaws data set as well as the in-house data set of neurosurgery. Thank you so much for listening. Thank you.
I'll just take this one off. Thank you very much.
Thank you. How did
Okay. Hello, this is the paper UCF video caption in the wild. In this work we introduced a new video captioning crime-related dataset because a lot of video captioning dataset exists, crime-related dataset exists, but no crime-related video captioning dataset. To create this dataset, we extracted the short clips duration up to 20 seconds from the UCF crime dataset that exists. The intuition that we used the short clips is that we thought that the crimes usually are of a short duration. This is an example, the frames of a video and its caption. Each caption describes the content of the video. Then, in order to check that the dataset we introduced is not rubbish, we proposed also a method, a multimodal transformer, to evaluate this dataset. We made an ablation study based on the fusion, on the phase of the fusion before the transformer encoder or after the transformer encoder, and how we will fuse the features. Two different features were employed, RGB features extracted from 2D CNN and motion features extracted from 3D CNN. Regarding the way that we fuse the features is a simple addition, the addition of the output of two multi-head attention layers, a concatenation and then downsampling a fully connected layer, and the concatenation of the output of two multi-head attention layers and their downsampling. As a conclusion, we had two conclusions. Multimodal models perform better than the unimodal one. The unimodal is by using only the RGB feature. And second, addition is better than concatenation because our two best methods, A2 and B1, are addition methods. And finally, we compared this method with some state-of-the-art methods. We achieved the best results on Meteor and Cedar metrics, and the second best results at Rouge metrics. That's it. Thank you.
Thank you very much.
Ok. Ah, je stresse. Oh, mais il faut. So in English. So lung cancer is quite frequent in. No, j'arrive pas. So in this work, we consider 3 patients were treated for lung cancer at Saint-Luc University Hospital at Brussels. And for each patient, we have a planning felicity, which is 10 breathing phases that represent an average breathing cycle. And from this felicity, we can create, using a data augmentation toolbox that we develop in our lab, 500 new 3D CT images. And from these images, we generate different digitally reconstructed radiographs that are given as input to a network that is able to reconstruct from this 2D image a 3D CT volume. So in this work, what you have to notice is that the training is patient-specific, which means that the training is performed independently for each patient. And two big methods are studied. The first one is single-angle training, where all the radiographs are taken from the same angle. And the other one is multi-angle training, where the radiographs are taken from different projection angle value. And here are the results. So you have here the ground truth 3D CT image compared to predicted images. And here you have the absolute value of the difference between these two images. So you can see that the difference is quite small, but there is area where the error is bigger. Here you have the error between the ground truth image and the prediction one, when the prediction is taken from projection that are not in the test set. And so the big contribution of this work is that we are able to reconstruct a 3D CT image from a 2D radiograph. And the goal is really to better localize the tumor during the treatment and to evaluate if the image can be used to do dose computation in order to assess if the dose is delivered at the right place in the right moment. That's all. Bon. Faudra peut-être couper quand je bug au début.
Brief. Yeah, sure. Thank you. Hello. So my name is Darshil. I am from IIIT Bangalore, India, and we are working on EEG analysis using deep learning. So EEG is actually used to measure the electrical activities inside the brain, and it can be used to measure different brain states such as emotion or identifying neurological disorders. Here, the idea is that the EEG signal is 1D time series data, and we can record the signals from the different regions of the brain. But ideally, the brain activation in the different region of the brain is lost in the 1D signal methods. So here we are trying to convert the EEG signals into EEG videos that could actually preserve the spatial, temporal, and spectral information. And then we are using interpolation method to generate videos from the signals. and then applying deep neural networks for classification. So we are using temporal convolution and a combination of temporal convolution and LSTM for the classification. We have performed this on EEG baselines, that is eyes open and eyes closed, and mental arithmetic to identify whether a person is at rest or some calculation state. And we are able to achieve higher accuracy than the current state of the art using preserving the spatial information. So like this is my work. Thank you for listening. Nobel Prize. Start? Thank you. Thank you.
Okay. We don't know how long. What should I do? I just introduce the whole work.
The whole work.
The whole work.
The whole work, yeah.
Okay. I will then. Hello everyone. I will introduce my work about Wi-Fi-based spatial temporal human action perception. The whole work is like this. We're using two devices. One is router, another is desktop. We're using this desktop or another computer to ping this router, and the router pounds the signals back. So the receiver receives the signal change to recognize what the people done between these two devices, because the person perform different actions can cause the signal change. So we're using the change of signals to recognize the person's actions. After then, we recorded it channel state information time series, which this is a time axis, another is a feature axis. This is just a data cube. But a person done features which sometimes last 1 second, sometimes last 2 seconds. So we're using different sliding windows to capture multi-scale channel state information data. So these data samples have different size. If we want to process them together, so we must deconvolution them into the same size. So using a three-dimensional deconvolution module to process the CSS samples into the same size, so it can be prepared to process it into another three-dimensional convolution network. This is just a residual module. So we developed this residual module into three-dimensional convolution modules. Several residual modules together can be capture the continuity of the three-dimensional channel state information data. After this, we can produce a confidence map. We're using the confidence map to convolute it with the input features. to got our self-attention maps. After this, we put it into fully connected layers to get the different actions. So this one works so well because it can concentrate the temporal information, spatial information, frequency information together into these cubes. So it can be works very better than the LSTM. So in this paper, the strength of the proposed is ability for the effective explanation of the multi-scale spatial temporal features and explicit maintenance of the self-attention feature. So experiment shows that STWN compare favorably against the comparative baselines. Thank you so much.
Thank you very much.
Thank you. Oh, I'm a little nervous. Okay. Yeah. Thank you.
Thank you very much.
Ouais, non, mais j'avais pas de... Small videos mostly point to point,
Okay, so our paper is about neural network compression and in particular about incremental neural network compression. And the use case for this incremental neural network compression is when you want to transmit your neural network while you are still training. And this can be, for example, the case if you want to directly apply it at the clients. Or, for example, another example is federated learning, where you have multiple clients that train and then transmits the updates to a server which does the averaging. And our method is based on ICNN, which is a coding standard for incremental neural network compression, which is currently developed by MTech. And specifically here, we modify the entropy coding part, which is called deep carbag. And in this deep carbag, the neural network-wise updates are entropy encoded, and for this, these updates are binarized. And specifically here, we consider the significance bin or flag which is coded, and
what we do is we modify the probability estimation for this significance bin. And an existing approach here or the approach that was used by ICIN before the adoption of our method was that only one context model, only the last update was considered to select the context model for this significance bin. So the question was left open if considering more updates can lead to further gains. And to evaluate this, we did some statistical analysis and had a look at the different weights and different layers and calculated the conditional probabilities for a significant weight update independence if any weight update before has been significant. And it turned out that this probability of a significant update changes considerably if any update before has been non-zero and significant. So what we simply did was adding a new context model for the case that any update before has been significant. And this then leads to a better probability estimation and average reduction of the bit rate of about 1 to 2.7%, considering the MPEG test condition which are used in standardization. So that's basically it. Thank you.
Thank you very much.
But the problem is just constraint. Instead, like the pictures can
Mais il faut tenir la caméra en se déplaçant. Même si le support en fait il est bien, mais tu me donnes en fait à ça. Ça en fait je te libère de ça. Et en vrai garde juste la caméra.
Ah ça s'applique ça.
Go. Hi, I'm Amy Riedman, and this is our paper on video analytics task-aware quad-tree partitioning and quantization for HEVC. So the basic idea here is we want to be doing compression for video analytics, and in particular we're focusing on face detection and pedestrian detection, and we're applying the HEVC, otherwise known as H.265 video compression system. So if we look at the block diagram here, our goal is to modify the encoder here for the video encoding in such a way that the output of our end-stage video analytics is more efficient and effective, and we have a higher mean average precision. So to do this, we're looking at using lightweight edge-based models to form weak predictions of where the objects of interest are, then doing some region of interest coding here to get an output frame that is better compressed for the purpose of doing video analytics. And the typical way of doing region of interest coding that we've seen a lot of times is ROI coding is by changing the quantization step size of a video encoder. And the main novelty here that we're doing is also changing the CU partitioning size, so changing the size of the blocks as we're changing the quantization parameters. So the weak prediction, we have a number of weak predictions coming out of here that say what's the likelihood of there being pedestrians in our different places, and if we think that there's an object or a pedestrian in a location, we'll do a finer partitioning of it. And this process, going from these weak predictions to here, is a deterministic process. But that changes the encoder. This task of choosing the CU partitions when we use an HM encoder, which is the sort of standard way to do the compression, it actually takes a fair amount of time. In our case, because this is a deterministic mapping, it's pretty instantaneous. So a couple of points of interest that we did a proof of concept first to show that we actually have two knobs going on here, two things that we can change. So if we change the quantization step size, we'll go from a high bit rate and high accuracy down to a very low bit rate and a low accuracy. But what's interesting is if we can fix the QP, or the quantizer step size, then we'll have a pretty wide range of bit rate without affecting the accuracy of the system. Whereas if we're down here in the low bit rate systems, we can again have an opposite, really. We're able to improve the accuracy pretty significantly without increasing the bit rate dramatically. And so this is a proof of concept that shows that we have these two knobs that we can adjust. So the method itself is, as I said, deterministic here. So given whether we think it's an object, the context around the region, say here, the object here, or some background region, we would assign a different size to the CU and also finer quantizers for the object, coarser quantizers for the background. And in terms of the results over here, so we looked at this in terms of both face detection using the IJBC data set on still frame encoding, as well as pedestrian detection on the Kitty data set using interframe video coding. And in general, we have, I'll just give you the high level, you can look at the details in the paper, but if we just use the off-the-shelf HM encoder, we're going to get this purple curve on the bottom, whereas we decrease the bit rate, the accuracy drops very slowly initially, but then the bit rate gets too large, it drops dramatically. On the other hand, if we know exactly where the pedestrians are and we apply our CU partitioning, so we use the ground truth, then we have this green curve where we have the same kind of behavior, but there's a significant gap in here. And so what we've explored then is the edge-based models, or using the full video analytics models, and also how confident are we in our predictions. And in general, we're able to get better performance by allowing weaker predictions, but in general, these edge-based models are as effective as the heavier models in terms of deciding where to spend your bits for this. And so that's a high-level version of the paper. Thanks.
Thank you very much.
So this work is basically on metal artifact detection on computed tomography images. So when patients have metallic implants in their body and they go for CT imaging, then this type of streaking artifact actually occurs in the image. So these streaking artifacts completely distort the information present in the CT images. So we need to restore these images to make it more diagnostic valuable. So in this work we have proposed one method. Actually we have proposed a new gated convolutional layer for this type of metallic artifact detection. So if you see, this metallic artifact is not uniform. So some location is distorted completely and some location is not distorted at all. So the location which is distorted, we can say it is an invalid pixel, and which is not distorted, we can say it is a valid pixel. So we propose to use a gating mechanism which will give more weightage to the valid pixel and less weightage to the invalid pixel. So our main target is to generate a mask M which will have a higher value or a value near to 1 for the valid pixel and value near to 0 for the invalid pixel. Now if you see in these cases, the valid pixel for any feature extractor, the valid pixel will have some higher activation value and the invalid pixel will have a lower activation value. So we can say the max M will be 1 if the intensity value at that location is a high among a small neighborhood. So based on this intuition, we propose this pull and exciting block. So what this block does is that it will first apply a max pooling layer to the input feature map. So after applying the max pooling layer, only the values which belongs to invalid pixel will be there in the max pool layer. So then after we apply again a max unpooling layer. So it will create a sparse feature map. The sparse feature map will contain only the values of the valid pixel. Now we will apply different scale of max pooling and max unpooling, and after applying we concatenated all the values in a single feature map. This single feature map is used inside our gated convolutional layer. So the gated convolution, first we have applied this pull and excite block in the input feature map that has created this 3D feature map. Then that is passed through a convolutional layer of 3 × 2 kernel size, and then after a sigmoidal operation we have got this mask M. Then this mask M is multiplied with the input feature map to generate this weighted feature map, and that is again passed through this normal convolutional layer to generate the output feature map. So this is a quite generic one. This convolutional module can be used in different architecture. In this study we have used the DNCNN architecture, which is also a common architecture for image restoration denoising. So in the DNCNN architecture, we replaced all the convolutional layer with our proposed gated convolutional layer, and we did one ablation where M1 is the basic DNCNN network and M2 is the let's talk about M3. M3 is our proposed network, and in case of M2 we have used one generic gated convolution layer which is proposed in the previous study. So based on our ablation, we found our method produced a very good result in compared to the other methods. So that is, we can see that improvement in PSNR is more than 1 dB. And also if you see the latent feature maps, we can see that in case of generic gated convolution, the weighting value is basically based on the semantic segmentation of the foreground and background. So that is, for foreground the masking value is high, for the background the masking value is very low. But in our case, the masking value is actually well correlated with the streaking artifacts. Along the streaking artifacts the masking value is low, and for the valid pixel the masking value is high. Now comparing with the state-of-the-art methods, we compared with CNN MAR, conditional GAN, Dudonet and other method. We found that our method performed better than the current state-of-the-art method, and also the visually these results are better than the other method. So that's all.
Thank you very much.
Yeah, you're welcome.
En fait, le but, c'est pas d'essayer d'être en bas, c'est de savoir le si jamais. So we are broadcasting live ICIP 2022 for the participants. Would you like to present your work for us?
Yeah.
For 3 minutes approximately.
All right. Approximately. All right.
All right. So you just put the mic here and on your pockets.
So do I have to having some introduction or just write?
It's good to introduce yourself so they know the university or something like that, and then you can start your work.
All right.
So
perfect.
Just put the mic on.
Start. All right. Hi everyone. I am Dat and I am from Germany. We are from FAU, Germany, and our work today is like lossless point cloud geometry, and you might already familiar with point cloud data. We are trying to compress the x, y, z coordinate, and for example, the most important thing why we are encode losslessly is the probability distribution of each point here being occupied. So we are doing that by the way. I will show you some example, like we have 3D point here, 1 point, 1 point, 1 point, and we want to predict whether the next point here in 3D space are occupied or not. And we are using the neural network, and most likely that because this 3 point create a line, and most likely that this point is being occupied. And using that information, we pass it to an arithmetic coder and encode the position here into bit stream. Yeah, and we compare our method with 1, 2, 3, 4 data set. The first one from Microsoft, the second one from MPEG, the next one is also from MPEG, and the last one is from Paulo University. And with the raw data set, we are having 3D point. For example, for 10-bit depth, we have 10 bit, 10 bit, 10 bit. So uncompressed data is 30 bits per point. And GPCC managed to get the number of bits per point down to 1. And we also compare our method against Bosonian, the gray one. They has a better rate compared to GPCC on all the 4 data set. And we are green here. We managed to compress the data down to less than 1 bit per point for MVUB and MPEG, and on the last 2 data set, which is sparser, as you can see here, the bits are a bit higher at 2 point something, and however, in terms of complexity, our method obtain having a lower complexity compared to Bosonian. However, compared to GPCC, we still having a higher encoding and decoding time. But we can improve that by having encoding all the block here in parallel instead of encode the block sequentially. Yeah, thanks.
Est-ce que tu m'entends bien? Je voulais vérifier s'il m'entendait bien. In English, du coup. Combien de temps ça doit durer à peu près? 2-3 minutes? 3-4 minutes? Ok. Tu me dis quand c'est bon. Okay, so I'm working on assessing the local quality of 3D reconstructed meshes. We are doing that in order to have a metric for next best view algorithm in order to help the general user to create 3D models of existing objects. So during my work we studied extrinsic metrics first, so those are metrics with reference model. Sorry. We studied those metrics because they were first designed for decimation algorithms or even for compression algorithms, and we wanted to see if they were able to detect problems or issues like noise, for example. And we can see here in the three first curves that that the curves are strictly monotonic, so that help us to see that those metrics can locally detect the deformations, but also to quantify the deformation on the models. But when we are doing 3D reconstruction, actually we don't have reference models, so we looked at intrinsic metrics, so without reference. The first one is the PLR, the plane local roughness, that is a reprojection error to the plane. And then we have mean curvature, and we proposed the quadric local roughness, that is the error of reprojection to a quadric. Those metrics, first we checked that those metrics were having high responses on the deformed areas of our model. So that's the case, but the problem is when we see the raw responses of our metrics, they are responding on the defaults. We can see it here, for example, but also on geometry. For example, we didn't made any difference on the beard here, but we have responses of the metrics. So all the objective now for my future work is to find a way to combine those metrics in order to be able to separate between what is actually noise and what is pure geometry of the model. And we also want to add other information such as the texture, for example, because it is really important in 3D reconstruction, especially with multi-view stereo algorithm. And that's it. Thank you.
C'est pourquoi. C'est bon? Oui. Voilà, merci beaucoup. Merci à vous.
Is it on? Can you hear me? Well, is it fine? Test sound. 1, 2, 3. Great, so I'm going to start. My name is João. I'm from University of Beira Interior, and I'm going to present, summarize the paper, Subjective Quality Evaluation of Point Cloud Coding Solutions with 3D stereoscopic visualization. So basically, point clouds, they have a lot of data, so we need to have efficient ways to compress them, and we need to have efficient ways of evaluating them. So our model, we create videos of it with targeting specific bit rates of the codecs. The codecs we choose are MPEGs, VPCC, and GPCC. VPCC stands for Video Point Cloud Compression, and GPCC for Geometry Point Cloud Compression. We also chose RSTL-PCC, which is Resolution Scalable Deep Learning Point Cloud Coding, which is a deep learning solution, and Google Draco, because Draco is more targeted for meshes than for point clouds. And so we also compute for different objective quality metrics. Here you can see the results of our subjective evaluation. We had 16 participants. You can see across the evaluation that VPCC is the best performing codec. With only this exception, in this case, the point cloud is really sparse. So VPCC has lots of trouble encoding it, and it's surpassed by GPCC. Here we can also see that the Draco, when encoding point clouds, it creates very high bit rates. So it's really difficult to compare them with this. So here we have the correlations for our for both evaluations, for the 2D evaluation and the 3D evaluation. You can see that the correlations are quite high. Without linear fitting, Pearson correlation is 0.882 and Spearman is 0.893. With linear fitting, it goes up a bit. The Pearson goes to 0.890 and the Spearman to 0.884. We also conducted Kruskal-Wallis tests. If the p-values are below 0.05, it means that there are statistical differences between the evaluations. We tested it for each content individually, for each codec. The global value, the global p-value was 0.71, so it had no statistical differences whatsoever, the evaluation. Here we have the objective evaluation. Is there a problem? Okay. This is the objective evaluation. So we computed PSNR-D1, PSNR-D2, Point SSIM and PCQM. You can see, and this is the results. These are the results for the 3D evaluation and for the 2D evaluation. We can see that PCQM achieved the highest performance with the Pearson correlation score of 0.93 and the Spearman rank of 0.92. It was slightly lower than the 2D evaluation, where it reached the Pearson of 0.944 and the Spearman correlation 0.928. So these are very small differences. And so basically the conclusion of our work is that there are no statistical differences between conducting subjective evaluation with 2D and 3D. But in the 3D environment, people find it more enjoyable since you can see the point clouds, there is a depth perception. So they're just happier in general if conducting the evaluation. And we also noted that the VPCC is the best performing codec and that PCQM was the best performing metric for these evaluations. Thank you.
Thank you very much.
Yeah. So, is it unmute?
Good to go? Okay. So hello everyone, my name is Sam van Damme, PhD researcher at Ghent University and IMEC, and here I will present my poster on clustering-based psychometric neuroreference quality model for a point cloud video. So the work is all about subjective perception of two-dimensional video with point cloud content in it. Basically, the motivation for this work is if you have point clouds, these are uncompressed in bandwidth requirements of gigabits per second, which is of course unfeasible in nowadays networks. So we need compression, and when we say compression, we are affecting quality and quality of experience. Subjective evaluations for this are rather expensive and time consuming, so we would actually like an objective and preferably a real-time metric to monitor this, this quality in real time. So we identified three challenges to do this. First of all, it should be near real time, which brings us to objectively friendly non-reference metrics. And we would also like a high correlation to subjective perception, which of course then we need a highly accurate full reference benchmark and a model to relate the former to the latter. And a third challenge we identified is that we would like to adapt to new types of content for which a clustering-based mechanism would be interesting. So what did we do? We created a very straightforward KNN clustering mechanism in which we actually optimized the number of clusters by maximizing the so-called silhouette score, which is a trade-off between the intra-distance in one cluster and the distance between multiple clusters on the other hand. And then in each cluster, we actually create a model by taking a sigmoidal or a so-called psychometric mapping of a linear combination of non-reference metrics, which includes two metrics of noise, two of blurriness, blockiness, spatial information, and just a straightforward bandwidth, which is basically what is shown here in the black part. And then in blue, for evaluation purposes, we also include the reference video on which we calculate VMAF as an objective benchmark, of which we have seen in a previous study that it actually correlates very well to mean opinion scores. And we use that for training and evaluation. So we created a data set for this using this four well-known point cloud objects, and we created 16 source videos out of it by using different setups and different camera movements. And then further, we also included multiple types of distortion in terms of VPCC encoding distortions and also dynamic streaming distortions. Which brings me to the results. We evaluated this by actually on each cluster taking out one particular video and then train on all the other videos and evaluate on the video we took out, and then do this for all the videos and average. And we actually see very high Pearson linear correlations for 3 out of 4 clusters. Only for the third cluster, it's a little lower in the range of 0.84. Which has two possible explanations. Because video 10 is isolated over here, we had to take out certain configurations as a test set, which of course means that during training not all configurations are seen. Second possible explanation is the fact that spatial information turned out to be much higher for this video than for the other videos, so it could be that it's just like a regular outlier in the data set. Nevertheless, we compared to the cases where we either discarded clustering or the sigmoidal mapping, or both. And we saw that both in terms of linear correlation or mean squared error, the combination of both actually showed the best results. So to conclude, we addressed our 3 challenges by creating a model consisting of 7 non-reference metrics, which are easy to calculate, with a high correlation to VMAF and thus to subjective perception, which we've shown before, and by including a KNN clustering mechanism to be able to adapt to new kinds of content, which concludes my presentation. Thank you very much.
Okay, so yes, I will present our work here on privacy-friendly or privacy-friendly approaches on salient behavior recognition. And I'm Thomas from Fraunhofer Institute for Optronics System Technologies and Image Exploitation from Germany. And what we are working for is actually motivated by the German or the European GDPR. So we are working on an assisting system that helps police officers to recognize crucial situations within the application of CCTV cameras. And our approach is to use skeleton sequences, which was also done by other authors like the MPET-RNN and GEPC. And the idea is to have sequences of skeletons which are abstract representations of persons behaving in some certain kind. And on this level, we extract the information from these skeleton sequences. We have a certain neural network architecture, an encoder-decoder based or an autoencoder based two-branch approach, which learns how people are normally behaving, but also how people are behaving in the salient way, because we have some salient samples. And as we can see here, our approach is outperforming the approaches already existing, which is mainly due to the additional second branch that has or introduces some kind of informedness. And still, you can see that there is a quite big gap to a perfect system. So the system itself performs good, let's say it like that, but there's still lots of work to do since the behavior of persons is not that easy to differentiate in its good behavior or it's a salient behavior or a non-salient behavior. And the major problem here is that the whole performance, the whole idea does only work when we have a certain quality of skeleton sequences, and therefore you need to have a very good pose estimator who generates these skeletons, these person poses, in order to have a good basis for the final evaluation. And as you can see on the results here, one might wonder on frame level, meaning in a certain situation the system would say, okay, there happened something important or salient, whereas on the instance level the performance is always below or lower than the frame level. This is mostly due to situations where people come close together, where the skeleton pose estimation suffers. There are persons missing, the skeletons are collapsing, and in this situation then our model still recognizes that there happened something, but this is mostly due to the collapsation itself, and not by the architecture we proposed. So as I said, major problem that still needs work on for the future is the whole part of the robust person pose estimation in order to generate the skeletons. Yeah, thank you. This,
Hello, my name is Fabio Faria. I'm presenting my work, Mix-Based Deep Metric Learning Approach for Incomplete Supervision. In this work, the main idea is how can you learn more for less. No? Here in this work, we use two different techniques from literature. The nearest neighbor Gaussian kernel, it's deep metric learning approach, NCA-based approach, and we have the pre-training CNN here. We extracted these features and we projecting the other space in the Gaussian kernel space, and in this new space we compute the probability X data belongs to each classes. In the other technique existing in literature, we have the mix-up. Mix-up is the virtual data augmentation approach based on the convex interpolation operation, and we have two different images. 100% of the cat here, and we have the other image in the 100% of belongs to dog class. We interpolate by the lambda value. For example, the .7, we have the resulting mixed image. We use this image to compute the mix-up loss, and the lambda plus cross entropy y hat belongs to cat plus the 1 minus lambda plus cross entropy y hat belongs to dog. We have two different techniques from literature. We combine them to create three different new losses. 1, 2, and 3. The number one is the simple combination, the loss NNGK plus the mix-up, and this second approach, that's our main contribution of this work. We have the new approach. We have the encapsulate the NNGK approach by the mix-up loss function, and the third one, we have the combination of the previous losses. Here we have the how can we imagine the feature space work. The first one, we have the pre-trained CNN samples and two different classes, the blue and yellow, and here we have the NNGK, just one approach. We have the NNGK space. Here we have the mix-up space, is a convex interpolation operation approach here. And this is a virtual data augmentation approach from the literature. And our contribution is the encapsulate this approach, NNGK, by the mix-up loss function. The main idea is we create the new images in the other space, compute the probability in the other space, and then we compute the loss mix-up approach. In our experiment, we performed two different scenarios. Incomplete supervised scenarios, what we have only 10% of the training set to train the CNN, or the training all of the deep metric learning approach, and we have the other scenario. Complete supervision scenario is the traditional image classification. We have different baseline approach from literature, from the ICIP conference, CVPR, NIPS, etc. We have 4 different data sets for incomplete supervision scenario, 3 different data sets for complete supervision scenarios. Finally, we have our performance experiments here. In complete supervision, we achieve excellent results when we compare our approach with against a loss deep metric learning approach and relate good relative gains when we compare our approach against the original two techniques. In our experiments, I need to comment about the CFAR 100. Our relative gain is 51% of our approach against the best deep metric learning in literature triplets. And when we compared our approach against the original approach from literature, we achieved 27% of the improvement. Now we have the other scenario, the complete supervision or the traditional image classification. Here, we'd like to know if our new proposal improve the original end-to-end GK approach. And here we observe that our approach improve, our three approaches improve the original approach. 3% of the flowers 102, cars 7% around, and leaf snap field, we improve almost 3%. And that's our paper. And please scan our code. And we have here our code is available on the GitHub repository. Thank you very much.